All right, this video is going to be a quick walkthrough of the apparent weight key. This was the homework that was due today. Um, First problem, 10 kilogram box, accelerating upwards in an elevator. The acceleration is 2 meters per second squared. So draw a free body diagram. We've got the normal force up supporting the box. We've got the weight of the box downwards, and we've got an acceleration upwards of 2 meters per second squared. Sum of the forces, as always, is equal to m times a. This is a non-zero acceleration, so we can't get rid of that. And the sum of the forces is the normal force up and the force of gravity down. So force of gravity is, of course, mg. So normal force minus mg, just to solve for the normal force, which is the apparent weight. Add mg to both sides, so I get ma plus mg on the left equal to the normal force. Factored out the m here just for simplicity and plugging in numbers. 10 kilograms times 12 meters per second squared, so 120 newtons there. And that is, of course, heavier than the actual weight. The box weighs 10 kilograms, or it's a mass of 10 kilograms, which means it weighs 100 newtons. But the scale is showing 120, so it is showing up heavier than it actually is. 60 kilogram woman in an elevator. The elevator is moving downward at 3 meters per second squared. So similar picture, normal force up, weight down, but the acceleration in this case is down. Same equation, sum of the forces is ma. Same idea here, sum of the forces is the normal minus the weight. And if we solve for the normal force, we get the same thing. It's the mass times the acceleration plus g. And in this case, the acceleration is a negative number. So we've got 10 minus 3 in parentheses, 7 meters per second squared times 60 kilograms. That gets us 420 newtons, which is lighter than the woman's actual weight. Because she's 60 kilograms, she would weigh 600 newtons. The next problem, 50 kilogram boy in an elevator. The elevator is moving at a constant speed. That means it has an acceleration of 0. That means the sum of the forces is still equal to ma, but a is 0, so the sum of the forces must be 0, which means the normal force minus the weight must be 0, which means the normal force must be equal to the weight. So the normal force, or the apparent weight of the boy, is 500 newtons, which is his actual weight. Next problem, a little bit trickier. We've got Samantha standing on a scale in an elevator, and she sees only 45% of the weight she measured in the morning at home. We assume at home she stands on her scale and sees her actual weight, mg. So now when she's in the elevator, she's seeing 45% of that. She's seeing 45% of mg. So her normal force, or her apparent weight, is equal to 0.45 times mg, 45% of what she saw in the morning. So we know our normal force here. We look at the sum of forces, of course, has to add up to ma. We don't know a in this case, but we do know that her normal force is 0.45 mg. And of course, that is upwards. Then we have her actual weight downwards, which is mg. It turns out we got an m in every term here, so we can get rid of all those m's. We can divide through by m, and we get the acceleration is equal to 0.45 g minus 1 g. So 0.45 minus 1 would give us negative 0.55 g. You could leave it there, or you could plug in the 10 and get that negative 0.55 g is equal to negative 5.5 meters per second squared, which means she's accelerating downwards. That makes sense because her weight is showing up to be much less of her actual weight. It's only 45% of her actual weight, so she must be accelerating downwards. Number 5, kind of an odd scenario here. Felipe is in the elevator before his physical. He's concerned about his weight. He's heading up to the 21st floor, and the scale reads 750 while the elevator is accelerating upwards at 2 meters per second squared. What will his actual weight be? Well, we got to find his mass to figure out what his actual weight will be. His actual weight will be mg, but we don't know his mass at this point. So our picture here, his apparent weight, or his normal force on his way up, is 750 newtons. That goes along with the acceleration upwards of 2 meters per second squared. And of course, the downward force on him is his weight, mg. Sum of the forces got to be equal to ma. Again, normal force up, mg down. We solve this for the normal force, and we've got ma plus mg. We can factor out an m. And then since we really want to solve for m, we divide both sides by ag. We get his normal force, or his apparent weight, divided by the acceleration plus g. That gives us his actual mass of 62.5 kilograms. And then if I want his weight, I'm going to take his mass and multiply by g, because his weight is mg. So mass times g, and that gives me his actual weight of 625 newtons. And then the helicopter, 70 kilogram package, suspended from a rope 5 meters long. Don't really care how long it is. Accelerates upwards at 5.2 meters per second squared. We're going to neglect air resistance. That's good. So the only forces we have are the force of the rope pulling up and the weight of the box pulling down. And we've got an acceleration upwards of 5.2 meters per second squared. So there's our free body diagram. Then we want to look at sum of the forces equation. So the sum of the forces has to be MA. We got a tension force up, mg down. We're going to solve for the tension force by moving mg to the other side. So we've got the force of tension is MA plus mg. We could factor if we wanted. 70 kilograms is the mass, 5.2 meters per second squared up, so positive, is the acceleration, and g is 10 meters per second squared. So we end up with a tension force of 1,064 newtons. It's a 700 Newton box. We needed some more tension to produce that upwards acceleration, so that makes sense. Getting close to the end here. If you stand on a scale in an elevator, as you often do, of course, it is your unlucky day and the cable supporting the elevator snaps. The entire elevator enters free fall with you inside it. What is the rate of acceleration of the elevator and you inside it? Well, if you're in free fall, then your acceleration would be g, or roughly 10 meters per second downward. So no work required there. It's just realizing what free fall is. What does your scale read? Draw a free body diagram and solve for your apparent weight. Remember, apparent weight is the normal force that the scale puts on you. Well, if you're accelerating downwards at 10 meters per second squared, normal force up, mg down, let's figure it out. Some of the forces has got to be equal to ma, and we got a normal force up and mg down for our forces. We want to solve for the normal force. However, the acceleration is actually minus g. It's downwards, and it's at a rate of g. So I could plug g in there if I wanted to. So ma is really the same as minus mg, in which case, the normal force, if I want to solve for it, I add mg to both sides, and we get 0. I could plug in numbers, of course. I could have plugged in numbers. Ma over here would be m times negative 10, and mg over here would be m times 10, and we'd add to both sides, and they would cancel out. So the numbers work too. You don't have to make this algebraic substitution. You could just plug in the numbers. So your apparent weight is 0. When you're in free fall, that's weightlessness, essentially, or simulated weightlessness. All right, last one. You're holding a tennis ball in your hand in problem 7. That means as you're falling in the elevator. As the falling elevator transports you to your untimely death, you let go of the tennis ball. What do you observe from your frame of reference? Does the ball fall to the floor of the elevator? I should say of the elevator. Or does it seem to hover in midair? The ball would seem to hover in the air as you fall, because the ball of the elevator, you're all accelerating downwards in free fall at the same rate. So relative to you, the ball doesn't move. So it would appear to hover, which violates Newton's laws because, of course, there is a net force down on the ball. But the problem here is your reference frame is not an inertial reference frame. Your reference frame is accelerating, so the ball does not appear to conform to Newton's laws of motion. It seems not to fall, even though it has a net force on it equal to its weight. Draw a free body diagram of the tennis ball. Well, there's the tennis ball, and the only thing acting on it is gravity. So the net force is the sum of the forces, which is mg. So it does have a net force of mg on it. So does your observation of the ball in the falling elevator seem to follow Newton's laws? We kind of said this already. No, it does not, because it has a net force on it, and yet it does not appear to accelerate to you, because you're accelerating alongside of it, which means you are not in an inertial reference frame. So that's the fancy physics language I'm looking for, an inertial reference frame. And that is why, since you are not in an inertial reference frame, you are in an accelerating reference frame, then Newton's laws don't appear to work. All right, that's it for that. I hope that helps. Let me know if you have any questions.